Come on. Okay. You're recording. Good. Okay. Fine. Yeah. So, okay. Forget about the skill. This is homework now, not skill session, but it doesn't really. So it's more sort of revision. Me neither. Okay. I can't see how. I don't mean on Keats. I mean on the screen. I mean, yeah. I mean, if you're not looking at the homework, what are you? What are you saying that you can? So to Quickang, what can you see on the screen, Quickang? If you want to write, because I'm curious. If you can't see this, what are you looking at on the screen? Okay, maybe I need to transfer the screen to or maybe that was it. Sorry, share screen probably, isn't it? Yeah. Okay. Okay, hopefully that works. Let me. Can you see it now?
Yes.
Okay, thanks. Yeah, sorry, I forgot to hit the push. So, yeah, I'll just cut that part of the video out later. Bit. Yeah. So, question one says, so I think on this course, we did look at American options for discrete time models, but you can also look at American options for continuous time models. Now, in general, there's quite a interesting and elaborate theory for that, but because it's not actually sort of in the lectures, we're not going to go fully into that. But we can consider a sort of simplification here. Well, an American option with a strike, American put option with a strike maturity of T2, which can be exercised early, similar in the binomial case, but only at the intermediate time T1. And again, we're assuming T1 is. So, I mean, in reality, I think, well, actually, maybe not for Bermudian swaps and things like that, but I mean, usually the classic American put option to look at under a continuous time model, like for instance Black-Scholes, you assume that you can exercise at any time, and that problem is harder because you have to. It's a so-called free boundary problem, which is well, I mean, I used to teach it sometimes, but it's beyond the scope of the course this year. But we can look at the simpler case where you just have the choice to exercise at that one single time. And if you don't exercise at that time, it's basically then just a European option from then on to the final time. So the question says, write down an integral expression for the price of the option at time 0 in terms of the price function of the corresponding European. So when I say corresponding, I mean having the same strike and the same maturity. So how can we price this thing? Well, as it's often becoming the case these days, we use an integral formula. So at the intermediate time T1, the option is worth the maximum of, so similar to the binomial trees, it's worth the maximum of the intrinsic value if we exercise, or the value of the European option, the European put option, because if we don't exercise, you're essentially left with a European option because you've missed your chance to exercise. So, as I said, similar to when in the binomial tree, you compare two prices, the maximum of the two of them. So, the value of this American put option at time T1 is equal to the discount. So, I'm not assuming, many questions recently I've always assumed interest rates are zero, but actually, for American options, usually for it to be interesting, you need a non-zero interest rate. Essentially, I think it can be proved that if the interest rate is zero, then the American is worth the same as the European, or something like that. So generally, to be interesting, but anyway, yeah. So this is the value of the American option at the intermediate time T1. I'm integrating over the usual log normal density of the stock price, and then this is the value. This is the payoff function, if you like. So think of it kind of as this is how much the American is worth. That. So think of it as like if you want, you can sell this American option at time T1 for this price because it's worth the maximum of its European price or its intrinsic value. But then the final part says write a corresponding formula for an American put option which can be exercised at multiple times, and they do have these things, particularly in interest rates. I think I mentioned this phrase earlier, but this is a funny name: Bermudan swaptions. I forget how they actually work exactly, but it's something in the interest rate world that has multiple exercise features like this. So, I mean, this is a bit fiddlier, but it's the same idea. You essentially use a backward induction. So, at time tn minus 2, the American option is worth, well, we express it in terms of what happens at the later time, tn minus 1. So you multiply it over the conditional density of stn minus 1, given where we are here, stn minus 2. And then it's the same thing. It's the max of k minus s there. But the price function you want there is the value, is the pstn minus 1, which is actually what you essentially, well, oh no, sorry, this is just a European option payoff. Or rather, this is just the price of a European put option. But the discounting factor is here because the time from tn minus 2 to t, so that should be tn minus 1, using my convention here, is that. And then it's the same formula again if you go back to the next time, that the value of this American option at time tn minus 3 is this discounting factor with the difference of the two times there. Conditional density of stn minus 2 given s, and the same kind of thing here, except now you've got tn minus 2, and in both integrals and this one we've got just a dummy variable s. So I wouldn't ask this part in an exam, but it's still, as you've seen with other questions, with the barrier option questions, getting comfortable with these kind of integral formula, integrating various payoff functions over the log normal density. And I should say, we've never actually wrote down an expression for the conditional density of the stock price at some earlier time, but it's very easily computed. Well, it essentially just comes directly from the usual density. I mean, the usual density is just a function like that, but it's essentially sort of condition. Well, but you can, because of what you remember, I've said that any option that we price on this course, its dependence on t and t is only through the difference tor equals t minus t. So this density will be the same as this density, but except that the S0 that would appear in this formula would get replaced with the earlier stock price time, essentially that thing. So yeah, it would just be the S0 gets replaced with stn minus 2 in that case. So we essentially already have this formula because we have the usual density, and we also have this rule, essentially because the log stock price has independent increments there, but I'm not going to go into that again. So, but it's fine. I mean, it's to just understand hopefully where the first formula comes in, when there is just one intermediate time. But yeah, if you keep going like this, you'll get back to the price of the American option at time 0. So it's like with the when we price an American put option on a binomial tree and we go backwards in time, it's that backward induction approach. So the final expression will look like this, where there's a discounting factor from time 0 to time t1. Again, the density of the stock was at t1 now, and again the maximum of the intrinsic value payoff there, and the sort of continuation value, if you like, which is the value of the American option, which has been computed from the previous iterate, which has been computed from the previous iterate, and blah blah blah. But don't worry too much. I was just trying to make the question a bit more involved, because you can explain that one in sort of 30 seconds. But so next one, another double barrier question, but where I kind of give you the answer and just ask you to say a little bit about it. So you can consider a double no touch option which has barriers at L and B, which are always active. So so it's not like the one last week where the barrier either stops or starts at some time. I'm assuming now a standard double no touch has a barrier L and an upper barrier U, and if you hit U, you die. and if you hit L, you die at any time from 0 to the final maturity T. Now, I won't be going into the theory of how you apply, because you essentially, well, there's two ways of doing it, but I think the more intuitive way is to actually use Fourier series. Now, great if some of you hopefully probably seen Fourier series. I mean, in the UK, it would be taught probably in the third year, or maybe actually the second year, I think. But I'm just going to give you a formula that comes from Fourier series. If you happen to remember that, how they work, brilliant, and you might even be able to go away and prove that. But yeah, so it turns out that the price function for a double no touch, if the current stock price is at T, is at S at the time T, is given by this expression here. Okay, so these phi n's are, so this is a Fourier series, so it has sine functions there. It has these lambda functions that you can think of as, as eigenvalues. But again, don't worry about that. The x here is just the log of the s that's there, and the a is the log of the natural log of the lower boundary, and the b is the natural log of the upper boundary, and tau is capital T minus T, the time to maturity. And there's also an expression for a, which I've got in the document, but I hid it just to make the question look not so confusing. But if you actually care what the an is, I can send you the formula. But anyway, so all I'm asking you to do is verify that the correct boundary conditions are satisfied along the barrier. And some other stuff. So if we look at phi n, yes, you got to be careful. So x is the log of the stock price. So we need to be considering x equals the log of which barrier, of the lower barrier L, but that's equal to a. What we have there. So you can see that if you put a in this formula, you get a minus a, which is 0, and the sine of 0 is 0. Sine of 0 is 0. So we do indeed see that every term in this series, although the series might look funky, every term here, phi n x, is 0, or I should say phi n of a is 0, and a corresponds to an S value of L. And it's similarly for phi n of B, which corresponds to a stock price value of capital B. The reason for that, it's not quite the same reason, but it's because you get n pi of b minus a over b minus a here, so you end up with sine of n pi. And for those of you who remember what the sine function looks like, it's every pi. Is that right? N pi. That must be 2 pi. Is that right? Yeah, I forgot. It's definitely true that sine of n pi is 0 for n in the integers, and that's definitely true. But I was just checking if I've drawn it right. Yeah, I think that must be right. So 2 pi and so on and so forth. Yeah. So for that reason, for this reason here, you do have to assume that that n is an integer, but n is an integer in this formula. That phi n of b is also 0. So even though you've got a messy formula, every term is 0 in that formula if the stock price is at level B. So we verified at least the two boundary conditions are satisfied. If we wanted to, we could also verify that each term in this series satisfies the Black-Scholes PDE. It shouldn't be too hard to do that. And therefore, at least heuristically, because you've got a sum of things that satisfy the Black-Scholes PDE, and the Black-Scholes PDE is linear, then this is a solution to the Black-Scholes PDE. There would be some rigor required to that, because that would work fine if you had a finite sum. If you've got an infinite sum, there would be some greater care needed to justify that. But I didn't actually ask that in the question. The one thing we can't, because I've just given you this formula from thin air, we can't trivially prove the correct terminal boundary condition. So we have to assume that I've calculated this correctly, or that I've calculated the Fourier series correctly. But what it does tell us is that, assuming that I have, so here I ask, I mean, I'm jumping ahead slightly, but here I ask, well, what is the sum from n equals 1 of a n phi n x? Well, that's this whole formula for the special case when tau is 0, so we can knock out that term and that term. Well, apart from the fact that there's still a half x there. So in that case, we would want to compute the left-hand side at final maturity. So the left-hand side at the final maturity, so I should always leave more space, is going to be, what's the value of this option at maturity? Well, it requires S to be greater than L and S to be less than B. I mean, I could write that in a tidier way, I suppose. So that is equal to e to the half x times this sum. So this is equal to e to the half x times the sum of an phi n of x. So this, as I said, this isn't the usual thing where we can easily verify that this is the correct boundary paper. You have to kind of trust this, and then assuming I got this, I calculate this. I mean, I did check it numerically last year. This tells us that this infinite series here multiplied by e to the half x is actually equal to this. And remember, if you're asking, well, I can't see any s on the right, so well, s is there because x is just log of s, so both sides do depend on. So, I mean, it must be the case based on this then if I divide both sides by that to get e to the minus a half x. And again, remember that x is actually just a function of, this is just a function of s. It must be that this is the Fourier series of this function here. And what does this indicator part look like? Well, of course, it just looks like well, yeah, let me do it with the straight line thing. So it's going to be a bit rubbish. Yeah, so at maturity, this thing is only worth 1 if you're strictly inside, if you're greater than, if S is greater than L and S is less than B. So I would put, because we assume that if you touch L, the appropriate thing to do is to draw the dot there with the understanding that if S is L or S is B, then the thing is worth 0, not 1. So we can draw this. You can go away and draw this infinite series, and I think it converges pretty quickly because you've got these exponential factors there, so they decay. Because in fact, it decays ridiculously quickly because you've got essentially e to the minus n squared here, apart from the gunk that's in front of it. So if you draw, I think I've got the picture, somewhere. So this was a plot of the value of the double no touch as a function of s when there's like a year left to maturity with some parameters here. So a barrier of 1.2 up, a barrier 1.2, lower barrier at 0.8. So of course, if the current stop price is at 0.8, the thing is worthless. If the current stop price is at 1.2, it's worthless. So the best place to be is kind of in the middle, some distance from both barriers. But it's open intuitive that it has this kind of U-shaped behavior like that. And if you get close to one barrier other, then the price starts decreasing as you get closer to the barrier. At expiry, we know, I mean, theoretically in limit, I mean, I just drew it, but I guess we can draw it again. We know we have this kind of behavior. But of course, in practice, you can only compute a finite number of terms in that Fourier series. So when you do that, I deliberately didn't choose too large a number because just to show this interesting behavior that there is this sort of issue that because at this point here, the double no touch is worth 0, but then immediately as you move to the limiting function is discontinuous because it looks like this. So you do get this slight numerical instability if you're only using finite number of terms in your Fourier, so it's a sort of little n equals 1 to n, for n is like, say, 20 or maybe 100 or something. So, but the larger you choose n, the smaller that is. But it's just much more noticeable when you're very close to maturity than when you're further away and everything looks nice and smooth. And so I think there was a final part of this question. What was that? Compute the Vega of this option at a general time t. So that just involves literally take it, although I mean again it might look like an exotic formula, but just computing the derivative of this with respect to sigma. So did I actually do that? I mean, I think that depends on sigma, and lambda n depends on sigma. So I don't know, did I do that? Looks like I did. So blah blah blah. Yeah, okay. So I think so the first contribution we would get is differentiating that with so you get minus a quarter sigma squared Tor. So minus a quarter sigma times Tor, but I've taken the Tor as a factor. And then the other contribution comes from leaving this alone, but differentiating this lot, which is inside the exponential with respect to sigma. So you would get a half sigma squared differentiate. It's just sigma, so pi squared sigma n squared. A half sigma squared there's become sigma. Otherwise, pi squared n squared b over a squared. And again, is there a factor of Tor? Yeah, and there was a factor of Tor. So the factor of Tor comes out both times. So I'll just put it there. So you can check you agree with that. But so this gives us a nice sort of semi-explicit formula, apart from the fact there's an infinite sum. But again, I imagine it converges pretty quickly. Yeah, it should do based on what we're seeing there. And we can plot that as well. And we get this kind of behavior that the Vega is negative, and this is intuitively fairly clear. So I think, because as I said, the best place to be is in the middle. The more volatility there is, the more intuitively, the more likely you are to hit either of the two barriers. So remember, Vega is the sensitivity of the option price with respect to sigma. So if sigma suddenly increases for some reason, even though, technically under the Black-Scholes model, sigma is not allowed to change, but we can still talk about the change in the option price if sigma were to change, or had been previously miscalculated or misestimated. So as I said, yes, if you've bought a double noted, you really don't want volatility, basically. So I think, did I say a bit more about that? So from the picture, it's intuitively. So the final part says explain why the option is negative gamma. Well, it's obvious that the option. Well, it depends on what was my definition of theta? I forget. Yeah, it's obvious. I think intuitively that the option has positive theta, because if everything stays the same, if the stock price, if the stock price is here, for instance, and then if the stock price doesn't move, but a small amount of time evolves, there's less time for the stock price to hit that barrier or that barrier. So therefore, time is your friend if you own a double noted. You basically just want to, sit around hoping for nothing to happen, basically. So the theta of this option, in other words, dp with dt, is greater than 0, but if we assume again, as we often do, that the interest rate is 0, the Black-Scholes PDE says that dp with dt plus a half sigma squared s squared d2p by ds squared is 0. So if the theta is positive, then the gamma must be negative. So that's what the final part of the question was asking. So so it's 3:30. What was question 3? Was there a question 3? Oh yeah, this one. Okay. So I think we've seen some of this before. So we consider now the displaced diffusion model, which looks like this. So note that it's a little bit like the Black-Scholes, except you have an affine function here with a linear term and a constant term, rather than just simply this type of term. If this term wasn't there, then it would be a geometric browning mode. So this is often used as an approximation to the slightly more realistic model. Well, you can have a constant there as well, but st to the beta dwt. So the intuition is that you draw a tangent line to the function s to the beta, which is a non-linear function of st, and I haven't put a sigma in because, but you essentially, if you draw a tangent line to this, so you're approximating this locally with a linear function that looks like this with an intercept and a slope, then you get to this model, and it's an approximation that you use a lot. At least when I used to work for banks, this approximation is used all the time in pricing interest rate products because it's a lot more tractable, as we will see. So for simplicity, I've assumed that the initial stop loss is 1, and it says solve this SDE and show that S can go negative if beta lies in 0, 1. And usually in practice, we do assume that beta is in 0, 1. You could include beta equals 1, but that is just geometric branding, so that's boring. We know about that. So the first bit we've seen already, I think, we let xt just equal to the thing that's in front of the dwt. Then from Ito's lemma, Ito's lemma is fairly easy here because this is just a linear function of st. There's no second derivative with respect to s, and there's no derivative with respect to t. So if you want to be pedantic about it, okay, we can consider f of s equals beta s plus 1 minus s. So f dash of s, the usual Ito lemma taking derivatives is beta f dash. Come on. Is 0. So when you do that, you get it's just simply f dash of st, which is beta times dst. But then we know that this is beta. What dst is xt dwt. So I'll just plug this iPad in. Or not. That's not working. Alright, what if it charges down? I'll have to go get another charger. But yeah, okay. I think it'll be on. So we recognize dst as xt times dwt. So x satisfies just to geometric branding, which is just the same as the Black-Scholes model with 0 drift and beta and sigma equals beta. So we know how to solve this. The solution to the SDE. So when I say solve this SDE, I mean actually explicitly solve it. So give an explicit expression for xt itself. So we know that xt is given by x0 e to the beta t minus a half beta squared t. So if you're struggling to remember, that comes from it. It's basically like the Black-Scholes model where s0 is e to the what is it, sigma wt plus mu minus a half sigma squared t. Except now sigma is beta and mu is 0. So mu is 0 because this doesn't have a drift, and sigma is beta because usually we'd have sigma there, but now we've got beta. So that gives us our explicit solution to x. And of course, if we've got the explicit solution to x, we have an explicit solution for s because x and s have a very simple relationship. We can get from x to st, xt divided by beta minus 1 minus beta is st. Anyway, and then the second part says, show that s can go negative if beta is in this range. So if so let's consider the possibility that s might go negative. If s is 0, if s hits 0, then we see that xt must be equal to 1 minus beta. So the next question to ask yourself is, well, can x hit 1 minus beta? Well, x0 is 1, and beta we're assuming is in 0, 1. So 1 minus beta is below 1. So as I've said, so this is below x0, which is 1 by assumption. So x certainly can hit 1 minus beta because it's also, I should say, greater than 0 because beta is in 0, 1. So we've got a number here which is below x0 but is above 0. And why do we know that? In fact, x will definitely hit this at some point before t is infinity, because as we've seen before, the log of x from Ito's lemma, as I said before, has is that on the screen? That's weird, isn't it? Text something grass, yeah. Oh, that's strange. But yeah, I don't know what that's fine. But anyway, is that gone? No, okay. Anyway, yeah. So yeah, the log of xt tends to minus infinity because log xt has a negative drift. I mean, the drift specifically would be d of log of xt would be minus half beta squared dt plus beta dwt. The rule is always that it's the original drift here minus a half times the volatility squared. Yeah, so I mean that's how I'm able to remember that without actually going away and improving it. So the log of xt tends to minus with it because this has an overall negative trend. So if log xt is tending to minus infinity, xt is tending to 0. If it's tending to 0, I mean obviously it's going to fluctuate a bit, but it's going to be like this kind of behaviour. I mean, it is actually a martingale as well, which is strange, but it still nevertheless tends to 0 eventually. So in particular, it's going to hit 1 minus beta at some point. So when it hits 1 minus beta, that corresponds. Well, when it goes below 1 minus beta, that corresponds to s going below 0. So it's one drawback of this model, although it's quite easy to solve this SDE. It's not so realistic that ST can go negative. But if the maturity is small, then the probability of that happening is quite small. So it still can be quite a useful approximation. It's a bit of an ugly approximation, but it's still quite a practically useful one. So anyway, that's the end of that question. And the last one, yeah. So I needed to write, so it says consider the Heston model, but I haven't actually written out the Heston model. So this is what we call a stochastic volatility model. So one of the projects you'll see next summer deals with this model. So it'd be square root of VT ST dw1t. So it's an extension of the Black-Scholes model where the volatility is not constant anymore, but itself follows its own stochastic process. So we have this dvt process that follows this SDE, which we've probably seen in a homework question at some point, I think. But so we have two Brownian motions now, which are correlated. I won't go into that, but you should be learning about that kind of how you can generate two correlated Brownian motions on FMO6, assuming you're doing that. And by correlated, I mean you can set up two Brownian. W1 and W2 are Brownian motions, and it's also true that the expected value of W1t times the expected value of W2t is equal to rho t. But I won't go into the detail. I'm not going to need it. But otherwise, yeah, this question is like, for the Black-Scholes model, this would just be the usual sigma. But now it's the square root of VT, where VT we can think of it as the instantaneous volatility squared because we square root it here, and VT itself follows this ST, so it has a mean reverting term here. So if V goes above this reference level theta, then it tends to get pulled back down. If V goes below theta, it goes back up. A bit like how interest rates tend to mean revert. If interest rates go too high, the governments tend to correct, do something to the economy to make them come back down, and vice versa. And you've got sigma times the square. So sigma, there's a constant sigma now which appears here instead of here. And no, you've got the square root of VT there, but you can show that VT will not go negative. So that can't happen, so that this doesn't cause a problem. There is a condition for this model. It says that if 2 kappa theta over sigma squared minus 1 is greater than 0, then in fact V cannot hit 0 ever. But if if this condition is violated, if it's not satisfied, then V can hit 0, but it then moves away from 0 again. Well, it moves away from 0 if kappa is great. So we always assume that kappa is greater than or equal to 0 because it doesn't make sense for it to be negative. But if kappa is greater than 0, then you can see that if V is at 0 or very close to 0, this term becomes irrelevant because this term is essentially 0. This term was also essentially 0. So when V is very close to 0, V actually behaves just like an ODE. It's just dV equals kappa theta minus V dt. And because I'm saying ODE, I'm actually just going to write it in a more suggestive way, just as that. So, sorry, is it even that? Yeah, okay, but actually, I mean, but I'm saying that V is 0 as well, so we can say even more than that and just say, well, it's in some sense approximately just kappa theta dt. So if kappa, the model, so as long as kappa, well, okay, so as long as kappa times theta is greater than 0, the process starts. If the process does hit 0, the process starts moving away from 0 again because this drift is positive, and swamps the small volatility. But I'm going off at a tangent there, anyway. But nevertheless, as I said, this is quite an important model, and one of your summer project choices is on this model. So it's good. It's a good one for you to be aware of. So the question is then looking at these so-called VIX contracts on this Hester model, which actually are options not on the stock price as we usually consider, but are options that are essentially just on what the V process does. So the VIX squared is defined to be this conditional expectation. It's essentially the average from T to T plus delta. So by average, I mean because you're integrating VU du, but dividing by the length of time between T and T plus delta. So this is the average, the expectation rather, of the average of VU conditioned at time T. So again, V is non-negative. So as I said last time, you can interchange the expectation and the integral to take that inside. It's that Fubini theorem again that we looked at last week. So you can write this VIX squared. So the thing you actually care about is VIX T, but the formula is such that VIX T squared is equal to this, which we've now just rewritten as this. No, okay, that's stupid. I think this and that are the same. Yeah, I meant to write that as a. I want to rewrite this expectation here as V of U minus T given V0 equals VT. Sure, I had that there. I must have accidentally deleted it. Yeah, okay. So it's the same thing here as with Black-Scholes. We're looking at the expectation of VU given VT, but this is all that matters, as I said before. I mean, again, because this SD doesn't have any time dependence in the coefficient, is the time difference between T and U. So this expectation is the same as the expectation of V at the time U minus T, which is positive, given that V0 is equal to VT. So all you have to do is actually calculate a formula to make some further for essentially just E of VT at time 0, because you can easily perform this translation to get from that to an expectation of this form with a VU there and given a VT there. So how do we do that? Well, the SDE, when we integrate it for VT, looks like this. Remember, any SD, you write an SD, but this is really just, it's meaningless on its own. This is just a shorthand for this, really, that we have a V process which satisfies this integral equation, if you like. So one thing is that for this question, we will actually be ignoring the first Brownian motion. We don't care, because the options that we're considering, we'll be considering options on the VIX. And I should say these VIX options are very popular, and it's got a very active research area at the moment as well about how to price these options and how to fit models to it. So it's quite an interesting and topical thing to look at as part of that project, in the final part of that project. But what I'm saying is that we can we can integrate OSD here, and we know that the expected value of VT is just, well, V0 is just constant plus the expected values plus the expected values. But this is a stochastic integral, and as we've said before, well, at least at your level in 99.9% of the cases, stochastic integrals have zero expectation. I mean, the general rule for if you have a stochastic integral form HSTWS expectation, and you want to ask, as I said, usually the expectation, it turns out, S from 0 to t is less than infinity. So you'd have to get technically to justify this, and anywhere else you want to use this trick, you'd have to go away and prove that this is true, but it could be proved. But assuming you've done that, then because this stochastic integral goes away, the expected value of VT is just V0 plus this. But again, using that Fubini to interchange the expectation and the integral, you get to this. But then we know that we can differentiate both sides then with respect to t, and use the fundamental theorem of calculus on the right hand side. So if we, for convenience, we let ft equal e of vt, i.e. what we have there, and then we then take the derivative of that, we get f dash t equals the derivative of this, but we've got an integral there, so the derivative precisely cancels out the integral by the fundamental theorem of calculus, and you're left with the integrand evaluated at t. So e of vt is actually the solution, or if you want an expression for this, it's the solution to a simple ordinary differential equation. And you can solve this ODE as follows: ft equals that. So here's where I wrote this, but yeah, I knew I'd written this somewhere. So as I said, but what we know, so we now have an expression here. This is e of vt, just to clarify that. E of vt is equal to what we have here. But we need to be able to compute e of vu given vt. But for that, we just have to look at this formula, as I said, and replace t by the time difference. The time difference here is from t to u. So it's so e of vu given vt is just the same formula, but with t replaced by u minus t, and v0 replaced by the earlier of the two times, which is vt. So here's our fairly simple, explicit formula for e vu given vt. Which appeared, why do we care? Well, it appeared back here in our expression for this Vic squared. So, but we also still have an integral here. So this is what, if we now, usually when we have a maturity of an option, we use capital T. So if I rewrite this expression, this whole thing here, but just setting little t equal to capital T, I now get Vic t squared is equal to 1 over delta times that integral. That's the same, and then that expectation that I've just computed. But we can compute this integral explicitly as well, because vt, although it's random, it does not depend on u. All we really care about is the u, because it's integral with respect to u, and the only u dependency is just this simple exponential. So when you do that, you have to be a bit careful about it. You end up with, well, I probably did this, I was probably cheated and did this in Mathematica. Obviously you've got to, compute the indefinite integral. The theta term there won't have any contribution. So, the indefinite integral, if I can even do this in my head, would be, what is it, minus 1 over kappa, isn't it? E to the minus kappa u minus t vt, which is random, minus theta. But then you've got to evaluate this at t, at u is t and t is delta. So, well, you can check this yourself, but you should get this is the answer. But the main moral of the story is that you can note that this formula is just an affine function, i.e. it's a linear function plus a constant term in terms of its dependence on vt. So constant times vt plus, constant apart from the fact that it depends on delta, plus a constant term here. So we can write this just simply as an easier way to remember is that the Vic t squared for this Hester model is just this affine function of vt itself. So if you want to price, a Vic's option has a payoff of Vic's t minus k, and the maximum of that and yeah, the max of the user, the maximum of it pays VIX minus K if VIX is greater than K and 0 otherwise. So if you wanted to price that, you'd price it in the usual way as the expectation. Well, you'd be assuming that you're already working under a risk neutral measure. But then another thing, this was referencing a formula in another document. But why is this handy? Well, it means you can price a VIX option just simply as an expectation of an affine function. Well, it's a square root because this is VIX squared. So, but we typically care about options on the VIX, not on VIX squared. So it's the expectation of the square root of A of VT plus B. But there is a formula for the density of VT, which is known as well. So you can rewrite this expectation as an integral of this form, square root of AV, where now V is a dummy variable times the density of P. And I have that in another document. It's just removed there. So maybe I'll copy that in. So this is quite a nice thing to compute for the project, that you have this you still have to compute this numerical integral, as a numerical integral, but you can approximate that as a finite sum of the form. A sum of the function evaluated at certain v values vi with certain weights, and those weights and v's can be chosen optimally using this thing called Gaussian quadrature. So no, you do not need to simulate the S process itself here. You only need the second parameter, because we're not actually looking at the stock price directly here. And you can also price the VIX future, which just corresponds to the VIX option when K is 0. So the VIX future is simply worth the expected value of the square root of A VT plus B without any K, which actually is what I wrote here by accident, but whereas here I meant to write this minus K and plus. And you can also define the implied volatility of a VIX option as well. So that's just that's the end of that skill session then. So that it's just a few more practice questions plus some new ideas that may help you on some of the other courses as well and for the project. So any questions about any of that stuff, or anything else? Okay, so as soon as I find out about the replacement what is it, skill session, I'll let you know. So when will homework 7? So I can put this homework up on Keats now. I still need to edit a few things on skill session 8. It's getting quite difficult at this point now to come up with any more new questions, but this homework will be up right after this, because I have to put it up anyway for the tutors to see. But I'll let you know when the skill session is up. But obviously that won't even be taking place. I can put the document before, but the actual video and live session won't be taking place till later in the week. So otherwise, so I guess I'll see you later in the week then. And I think only one of you is really emailing me about the course at all, just only one guy. So you really should, more of you should be emailing me than just him, given I'm sure there's like over 100 of you on the course. So don't suffer in silence. If you suffer in silence, that's how to be in the third of students who will probably fail the course in January. So I'm just warning you about that. All right, there is a question, and so question 3, analysis for the final paragraph. I've said this before, not even forget about this. I've said before that in general, if you have let's say the black shoulder, let's just work under the physical measure, for instance. So it's mu st gt plus sigma st gwt. When you apply Euclid's lemma to that, you get the d log xt. As I said earlier, is mu. The rule is always you just take the drift that's in front of the st, and it's minus a half the volatility term, but again without the sigma t, dt plus sigma dwt. But then if this mu minus half sigma squared is less than 0, which it certainly will be if mu is 0, then the overall trend of the log of the process is negative. Now, that's not a completely rigorous proof. I think in one of the homework questions we showed, we did give a nice proof somewhere that I think ST tends to 0 in probability by actually looking at the Black-Scholes for the price of the formula for the price of that was quite a nice proof. It would be ST something tending to something in probability doesn't always imply that it tends to 0 almost surely. So I'd have to think about the nicest way to go from proving that SG tends to 0 in probability. I thought I had a proof early on in the course, but I think I had to remove the question at the last second because I noticed that it wasn't completely justified. But we have proved that ST when if for the stock price, if the stock has 0 drift, then and it follows geometric bound, then ST tends to 0 in probability. I think it was definitely the first question on one of the home. It was the one when Marcus was observing, although maybe he didn't know he was observing. Yeah, okay, a few weeks back. So it's nothing really particular. This question, it's this general rule that you should be comfortable with. That if you have geometric Brownian measure with a drift of mu, then the log of that process has a drift of mu minus a half sigma squared, if sigma is the thing that is in terms that follow the sigma. Of course, in this question here, there is no mu, so mu is 0, and sigma has been replaced by beta here, so you get minus a half beta squared there, but that's obviously negative. So hopefully that clarifies your question. And any other questions? Okay, so I'll hit stop on the record then.